March 1945. The Rhine River roars beneath a grey German sky, its waters churning with the memory of 1,000 years of warfare. This is the war's final barrier between the Allies and the heart of the Reich, a natural fortress that has stopped armies since the time of Caesar. Tanks idle at the riverbank, their engines silent, crews staring across the water at the twisted steel skeleton of what was once a bridge. The structure lies in ruins, now broken ribs of iron jutting from the current, like the bones of some ancient beast. They said it couldn't be done, that no army could build a bridge across the Rhine under fire, let alone in 2 days. But the Americans didn't wait. Within 48 hours, under constant bombardment, engineers built the impossible, a bridge so vital it would carry the weight of an army, and with it, the fall of Nazi Germany. This is the story of how ordinary men defied the river, the enemy, and the clock, and built victory plank by plank. Late March 1945. Hitler's Reich stands on the precipice of collapse, yet one final barrier remains, a natural fortress, stretching 0 kilometers across western Germany. The Rhine River, with its average width of 400 meters and current velocities reaching 4 meters per second during spring floods, represents not merely a geographical obstacle, but a strategic fulcrum upon which the entire European theater balances. For centuries, the Rhine had functioned as the demarcation line of empires, of armies, of fate itself. In 1945, it became the ultimate test of Allied engineering capacity and logistical supremacy. The river's strategic significance extended beyond its physical dimensions. Crossing it meant penetrating into the Ruhr Valley, which in 1944 produced approximately 60% of Germany's coal output and 50% of its steel production. Without the Ruhr, the Wehrmacht's industrial backbone would shatter irreparably. German High Command, recognizing this existential vulnerability, had systematically destroyed every Rhine crossing. The demolition program was comprehensive. 22 major bridges obliterated between September 1944 and March 1945, each destruction requiring between 800 and 400 kilograms of explosives, precisely placed to ensure complete structural collapse. The only exception emerged through fortune rather than planning: the surprise capture of the Ludendorff Bridge at Remagen on March 7th, which survived German demolition attempts and provided the first Allied toehold across the river. Yet Remagen represented a singular tactical opportunity, not a systemic solution. The bridge collapsed 10 days after capture, having sustained damage from both initial German demolition attempts and subsequent artillery bombardment. The fundamental challenge remained: could the Allies construct a bridge infrastructure capable of supporting armored divisions, structures engineered to bear 40-ton Sherman tanks and 70-ton tank destroyers, while operating under active enemy fire and completing construction within operational timelines, measured in hours, not weeks? General William Simpson's 9th Army, positioned near Wesel in coordination with British Field Marshal Montgomery's Operation Plunder, confronted this precise challenge. Montgomery's meticulous planning called for a two-pronged Rhine assault, a northern crossing supported by airborne operations and simultaneous American engineering operations to establish permanent bridge infrastructure. The operational parameters were unambiguous: construct a Class 40 pontoon bridge, military designation for structures supporting 40-ton vehicles spanning approximately 351 meters within a 48-hour window, while German artillery batteries maintained active targeting protocols. The question transcended simple engineering feasibility. It became a test of whether industrial logistics could overcome geographical determinism itself. March 24th, 1945:06:00 hours. Operation Plunder commences with an artillery barrage that transforms the pre-dawn darkness into a strobing hell of muzzle flashes. Across a 35-kilometer front, 3,411 artillery pieces, including 8-inch howitzers, 240mm guns, and British 25-pounders, deliver a preparatory bombardment calculated at 65261 rounds within the first hour. The mathematical precision is staggering. 1 artillery piece per 10 meters of frontage, a density of fire unprecedented in the Western theater. Within this orchestrated chaos, Colonel Mason J. Young, of the 164th Engineer Combat Battalion, receives orders that defy conventional engineering timelines. The directive originates from 9th Army headquarters, transmitted through standard field telephone lines, vulnerable to German interdiction. Construct a Class 40 treadway pontoon bridge, spanning 351.4 meters across the Rhine. At coordinates 51.6583 degrees north, 6.6167 degrees east, the Wesel crossing site, designated Bridge Site Alpha 7. Young gathers his battalion commanders in a hastily established command post 800 meters from the riverbank, close enough to hear the Wehrmacht's defensive artillery responding to the Allied barrage. The briefing materials spread across a makeshift table include hydrographic surveys of the Rhine's cross-sectional profile, structural load calculations for M4. 3 Sherman tanks, 33.3 tons, combat-loaded and tidal. Flow data indicating current velocities fluctuating between 3.2 and 4.1 meters per second, depending on recent rainfall patterns. The engineering parameters are explicit. Construct a 351.4 meter bridge using M1940 pneumatic pontoon units, each measuring 8.8 meters in length and capable of supporting 5.9 tons per unit when properly ballasted. The bridge superstructure will utilize treadway panels, steel sections weighing 82 kilograms, each interlocking to create a continuous roadway surface, capable of distributing vehicular loads across the pontoon foundation. Total material requirements: 40 pontoon units, 847, treadway panels, 3,2,0 meters of anchor cable, rated to 15-ton braking strength, and approximately 1,2,0,0 individual bolts, pins, and connecting. Hardware. Timeline allocation 48 hours from commencement to operational certification. The engineers exchange glances that require no verbal translation. Many served in the North African campaign, where constructing temporary bridges across wadis represented routine operations. Others participated in the Seine crossings the previous August, where German resistance had already fragmented into localized pockets. But the Rhine crossing presents variables that transform engineering from technical challenge into existential gamble. Consider the hydrological complexity alone. Unlike the Seine's maximum width of 200 meters at Paris, the Rhine at Wesel maintains year-round dimensions, exceeding 350 meters with depth profiles varying between 4.2 and 7.8 meters, depending on seasonal fluctuations. Spring melt from alpine tributaries increases discharge rates from baseline 2300 cubic meters per second to potential surge capacities of 6000 cubic meters per second. Each pontoon unit must withstand not merely static water resistance but dynamic hydraulic forces equivalent to 8.4 tons of lateral pressure per square meter of submerged surface area. Then overlay the tactical dimension. German artillery observers occupy elevated positions on the eastern bank, providing direct line of sight to any engineering operations. Wehrmacht doctrine, as outlined in captured Heeresdienstvorschrift field manuals, prescribes systematic interdiction of river crossing operations through pre-registered artillery fires, coordinated with available Luftwaffe strike assets. Intelligence estimates indicate German artillery concentration in the Wesel sector includes 105 mm howitzers, 150 mm guns, and potentially 170 mm K-18 cannons, with maximum effective ranges of 18 kilometers, sufficient to persist. Target not merely the bridge construction site, but staging areas, equipment, marshalling points, and approach routes. Colonel Young's response carries no theatrical drama, merely the flat pragmatism of industrial war. Gentlemen, we commence at 1,800 hours. The river doesn't care about our doubts, and neither does Berlin. Dismissed. They didn't know if completion within 48 hours was achievable. But operational uncertainty had long since ceased to function as grounds for hesitation. 1,800 hours. Darkness descends across the Rhine Valley as the 164th Engineer Combat Battalion initiates bridge construction protocols. The operational challenge transcends mere technical execution. It represents a fundamental inversion of military engineering doctrine. Standard U.S. Army Field Manual FM 5-6 Operations of Engineer Field Units stipulates that pontoon bridge construction should occur under conditions of tactical security, preferably during periods of enemy disengagement. The vessel crossing violates every baseline assumption. Construction commences under active artillery interdiction during hours of maximum visibility, vulnerability across a river whose hydrological characteristics alone would challenge, and peacetime engineering operations. The engineers deploy 1500-watt floodlights mounted on M4 high-speed tractor units, positioned at 45-meter intervals along the western bank. The illumination array generates approximately 180000 lumens of combined output, transforming the river surface into a theater of stark visibility. This lighting infrastructure serves dual functions, enabling precision work during nocturnal hours, while simultaneously creating target acquisition opportunities for German artillery observers, equipped with Zeiss 10x50 binoculars, capable of resolving human-scale targets at ranges exceeding 1200 meters under optimal lighting conditions. The Wehrmacht's response manifests within 12 minutes of initial floodlight activation. German artillery batteries, pre-positioned during the preceding weeks of defensive preparation, commence systematic interdiction fires. The incoming ordnance primarily consists of 105mm Leerfach 18 howitzer shells, each projectile weighing 14.81 kilograms, delivering high explosive payloads with lethal fragmentation, radii of 15 meters, and casualty-producing effects extending to 50 meters. Fire mission protocols target not the bridge structure itself, which remains non-existent during initial construction phases, but the staging areas, where pontoon units await deployment. Consider the acoustic environment, the percussive report of outgoing Allied counter-battery fire, the descending whistle of German shells traversing ballistic arcs, calculated at approximately 8 seconds flight time, from firing position to impact, the concussive detonations generating overpressure waves sufficient to rupture human eardrums at distances under 3 meters. Engineers operate within this kinetic cacophony, wearing standard M1 helmets, providing protection against fragmentation but minimal acoustic insulation. Their auditory perception reduced to distinguishing between outgoing Allied and incoming German fire through differential pitch recognition, developed through experiential learning rather than formal training protocols. The first pontoon section enters the water at 1,847 hours. Each M1940 pneumatic pontoon unit measures 8 meters in length, 1.65 meters in width, and when properly inflated to operational pressure of 0.21 kilograms per square centimeter, displaces sufficient water volume to generate 5.9 tons of buoyancy. The units are fabricated from rubberized canvas, reinforced with cotton duck fabric, vulnerable to puncture from shrapnel fragmentation, yet remarkably resilient under hydrodynamic stress. Engineers guide these sections into position using manila rope rated to 2 5-ton working loads, their hands immersed in Rhine water, maintaining temperatures of 6.7 degrees Celsius, cold enough to induce loss of manual dexterity within 8 to 12 minutes of continuous exposure. At 2,034 hours, a German 105mm shell achieves direct impact on pontoon Unit 7 during mid-river positioning. The detonation creates a water column, ejecting 847 kilograms of displaced Rhine water vertically to approximately 18 meters, while simultaneously puncturing the pontoon's forward flotation chamber. 3 engineers, Corporal James Hendricks, Private First Class Robert Yamamoto, and Private Donald Kessler, enter the water to prevent downstream drift of the damaged unit. Water temperature, combined with the physical exertion required to maneuver a 680-kilogram pontoon section against 3.8 meter per second current velocity, creates physiological stress conditions, approximating cold water immersion survival thresholds documented in U.S. Navy hypothermia research. The damaged pontoon is retrieved. A replacement unit enters deployment queue within 14 minutes. The construction sequence does not pause for casualty assessment or tactical reconsideration. The river continues its indifferent flow eastward, and the engineers continue their methodical advance across its surface, each bolt tightened, representing incremental progress, measured not in meters, but in the accumulated weight of industrial determination. The industrial machinery arrives at 7 hours on March 25th, transforming the riverbank into what military logistics doctrine terms a forward engineering depot, a designation that inadequately captures the scale of mechanical mobilization now unfolding. The 502nd Heavy Pontoon Battalion deploys equipment representing the culmination of American industrial standardization philosophy. Caterpillar D, 7 bulldozers generating 80 drawbar horsepower capable of moving 23.5 cubic meters of earth per hour. Link Belt LS 98 cranes with 9.1-ton lift capacities at 9.1-meter boom extensions, and Diamond T Model 980 over 981 12-ton cargo trucks, each vehicle's 14.6 6-liter Hercules DFXE diesel engine, producing 185 horsepower at 1/800 revolutions per minute. The mechanized infrastructure serves a specific doctrinal purpose, accelerating the bridge construction timeline through systematic modularization of structural components. This approach represents American engineering philosophy's fundamental divergence from European tradition, which historically emphasized permanent masonry construction over temporary tactical structures. The U.S. Army Corps of Engineers, drawing from Depression-era public works experience and wartime industrial scaling, developed standardized bridge components manufactured to tolerances of plus or minus 3.2 mm precision, sufficient to ensure interchangeability across units produced in facilities separated by continental distances. Consider the M1000 940 pontoon system's evolutionary lineage. Its design parameters emerged from 1,938 engineer board trials at Fort Belvoir, Virginia, where prototype testing identified optimal flotation characteristics, length-to-beam ratios of 5.331, compartmentalized inflation chambers, providing redundancy against combat damage, and rubberized canvas construction, enabling 68 kilogram weight per unit, light enough for 4-man teams to maneuver yet robust enough to withstand hydrodynamic pressures of 847 kilograms per square meter at operational current velocities. The assembly process operates through synchronized crew rotation protocols. First wave teams position pontoon units in precise alignment using surveying equipment, Wild T2 theodolites, accurate to 1 arc-second resolution, enabling angular measurements, translating to positional accuracy of 4.8 millimeters at 100-meter distances. Second wave teams install treadway panels, each 4.88-meter section, interlocking through male-female connector pins, requiring 203 Newton-meters of torque to achieve proper seating. Third wave teams tension anchor cables, calculating required cable angles through vector force decomposition. Upstream cables positioned at 37-degree angles to counteract current-induced lateral forces. Downstream cables at 22-degree angles to prevent pontoon rotation under asymmetric loading. The coordination encompasses approximately 1,847 personnel operating in overlapping 6-hour shifts, creating continuous 24-hour construction cycles. This workforce distribution reflects U.S. Army manpower allocation doctrine: 40% direct construction personnel, 35% material handling and logistics support, 15% security and traffic control, 10% command medical and administrative functions. The mathematical elegance is remarkable, each percentage point representing 18.47 individuals, each individual's labor output quantifiable through time-motion studies conducted at engineer training centers. Average bolt installation rate of 14.3 fasteners per minute. Treadway panel positioning, averaging 8.7 minutes per unit, including alignment verification. At 1,215 hours on March 25th, 30 hours into construction operations, the bridge achieves 73% structural completion, 256.5 meters of the required 351.4 meter span now extends across the Rhine. The structure's load-bearing capacity undergoes continuous verification through distributed weight testing. Engineer vehicles progressively traverse completed sections, while strain gauge instrumentation monitors pontoon displacement, treadway deflection, and cable tension distribution. The target specification requires supporting M26 Pershing heavy tanks, 41.7 metric tons, combat loaded with ground pressure of 0. 88 kilograms per square centimeter, distributed across track contact patches, totaling 4.6 square meters. The river beneath continues its indifferent flow, but the geometry of tactical possibility has fundamentally shifted. Steel superstructure now spans water that had for millennia divided continents. The Rhine yields incrementally to industrial will. German observation posts positioned along the eastern Rhine bank maintained continuous surveillance protocols throughout the bridge construction sequence, their intelligence-gathering apparatus representing a terminal paradox, methodical documentation of tactical impossibility unfolding in real time. Wehrmacht forward observers, equipped with standardized SF-14Z stereoscopic rangefinders optical instruments providing 1.5-meter range accuracy at 400.0-meter distances through dual 12x magnification eyepieces, transmitted systematic reports to LXXXVI Corps headquarters detailing construction progress with clinical precision. The German analytical framework revealed a fundamental cognitive dissonance between observed reality and doctrinal expectations. Wehrmacht engineering manuals, specifically Pionierdienstvorschrift specifications, developed from Rhine defensive studies conducted between 1943 to 1944 calculated minimum bridge construction timelines based on historical precedent, temporary pontoon crossings over rivers exceeding 300-meter width required between 96 to 144 hours under optimal conditions, defined as absence of enemy interdiction, daylight construction periods, and favorable hydrological parameters. The American operation violated every baseline assumption simultaneously, yet construction velocity accelerated rather than diminished under adverse conditions. Consider the intelligence reports transmitted through Wehrmacht signals infrastructure during the night of March 24th-25th. Oberst Heinrich Traut, commanding artillery elements of the 190th Infantry Division, documented observations indicating approximately 40 to 50 pontoon units deployed with mechanized crane support construction proceeding at estimated 7.3 meters per hour despite ongoing interdiction fires. The mathematical implication was stark at sustained velocity. Bridge completion would occur within the 48-hour operational window American forces had somehow designated as achievable. German counter-interdiction efforts mobilized available tactical assets within doctrinal response parameters. Luftwaffe Jagdgeschwader units operating from improvised airfields near Rheine and Handorf launched interdiction sorties utilizing Focke-Wulf FW-190 F-8 fighter bombers aircraft configured for ground attack missions. With underwing ETC-501 bomb racks capable of carrying SC-250 general-purpose bombs, delivering 125-kilogram high-explosive payloads. The tactical calculus appeared favorable. A single direct hit on the bridge's central span would sever the structure, necessitating reconstruction from both banks simultaneously and potentially doubling completion timelines. The Luftwaffe's operational reality, however, reflected systemic collapse rather than tactical capability. Allied air supremacy established through months of attritional combat, resulting in Luftwaffe fighter losses averaging 34.7% monthly attrition rates since January 1945, constrained German aviation to nocturnal operations under conditions of navigational uncertainty. More critically, Allied anti-aircraft infrastructure, including M51 Quad, 50 caliber machine gun mounts generating combined cyclic rates of 2200 rounds per minute per weapon system and 40 millimeters. Bofors automatic cannons with effective ceiling ranges of 3800 meters created interdiction envelopes, rendering low-altitude attack approaches tactically untenable. On March 25th, at 0423 hours 3 Phi 190 seconds penetrated Allied air defense perimeters. 2 aircraft were destroyed by anti-aircraft fire before achieving weapons release parameters. The third aircraft delivered a single SC-250 bomb that impacted 34 meters north of the bridge structure, creating a water column and concussive overpressure wave, but inflicting 0 structural damage. A young American corporal later identified through post-war historical documentation as James Mitchell of the 164th Engineer Combat Battalion recorded observations in a personal notebook recovered decades later. building faster than they can destroy. Feels like time's on our side for once, like watching a factory assembly line that happens to cross a river. The German observers continued their documentation, protocols, binoculars tracking each pontoon's placement, each treadway panel's installation. They were witnessing not merely a bridge's construction, but the mathematical expression of industrial warfare's ultimate logic when systemic capacity achieves sufficient magnitude. Individual tactical interventions become statistically irrelevant. The Rhine yields to industrial mathematics at precisely 1030 hours, on March 26, 19454, 7 hours and 14 minutes after construction commencement. This temporal precision represents more than mere schedule adherence. It demonstrates logistical synchronization, operating at scales that transform tactical engineering into strategic infrastructure deployment. Dawn breaks across the river valley, revealing the accumulated product of 1,128,000 man-hours of continuous labor, a 351 4-meter pontoon bridge, comprising 40 individual flotation units, 847 treadway panels, and approximately 12,000 discrete fastening components, each element positioned within tolerances, measuring 4.8 millimeters. The structure's completed mass totals 318 metric tons of steel rubberized canvas and connecting hardware, yet remains fundamentally buoyant, displacing sufficient Rhine water volume to generate 240 tons of upward force under static loading conditions. The engineers who position the final treadway sections operate in silence, born of physical exhaustion rather than ceremonial reverence. Medical documentation from 164th Engineer Combat Battalion aid stations indicates that by construction hour 46, approximately 73% of personnel exhibited symptoms consistent with acute fatigue syndrome, diminished motor coordination, impaired depth perception, and reduced cognitive processing velocity, averaging 28% below baseline performance metrics. Yet the work continues with mechanical precision, suggesting that habituated procedural memory can sustain complex technical operations even as higher-order executive functions deteriorate under sustained stress. The bridge's operational certification follows U.S. Army Corps of Engineers Protocol 74B progressive load testing under combat conditions. Initial verification employs a Willys MB Jeep curb weight 1247 kilograms, traversing the complete span at walking pace, while engineer observers monitor pontoon displacement through optical surveying equipment. Maximum observed deflection measures 8.3 centimeters at the structure's midpoint, well within the 15 centimeter tolerance specified for Class 40 bridges under distributed loading conditions. Subsequent test phases escalate vehicular mass systematically, M3 half-tracks at 9.3 tons M4, a 3 Sherman tanks at 33.3 tons, ultimately culminating in M26, Pershing heavy tanks at 41.7 tons. Each test iteration generates comprehensive data regarding load distribution mechanics, pontoon buoyancy response under asymmetric pressure, and treadway panel deflection characteristics. The mathematical elegance becomes apparent through comparative analysis. A 41.7-ton tank generates ground pressure of 0.88 kilograms per square centimeter across its track contact patches, yet when distributed across a pontoon bridge's flotation infrastructure, this concentrated force disperses into hydrodynamic pressure differentials of merely 0.13 kilograms per square centimeter below the threshold for inducing structural deformation in properly tensioned cable anchor systems. At 1,114 hours, operational certification achieves formal approval. The bridge transitions from engineering test article to tactical infrastructure, designated in 9th Army Logistics Protocols as Bridge Site Alpha 7 Class, 40 pontoon Rhine River kilometer 814. Within 23 minutes, the first combat elements begin crossing reconnaissance units of the 2nd Armored Division. Their M8 Greyhound armored cars advancing in column formation at 8 km/h velocities dictated by bridge traffic control protocols. The crossing becomes a continuous flow of mechanized warfare's material expression. By 1600 hours on March 26th, traffic volume achieves 847 vehicle movements per hour, a throughput density requiring vehicles to maintain 12.7 meter spacing intervals while traversing 351.4-meter span, creating a choreographed procession where each vehicle's Rhine crossing duration averages 2.8 minutes. The bridge itself exhibits remarkable dynamic stability, its pontoon foundation absorbing the oscillatory loads generated by tracked vehicle passage through distributed displacement across 40 individual flotation units. Each unit's buoyancy adjusting in real time to maintain structural equilibrium. The Rhine, which for 47 hours represented an engineering challenge quantifiable through hydrological parameters, structural calculations, and temporal constraints, has transformed into operational infrastructure. The river that stopped Julius Caesar's legions, that defined Charlemagne's empire, that anchored German defensive doctrine for 2 world wars, now functions as a highway carrying the mechanized instruments of strategic defeat eastward into the industrial heart of the collapsing Reich. The bridge at Wesel undergoes functional metamorphosis within its first operational day, transforming from tactical crossing point into strategic artery, sustaining an entire army's logistical metabolism. Between 1,114 hours on March 26th and 1,114 hours on March 27th, a precisely measured 24-hour interval, the structure facilitates 16438 vehicle crossings, translating to an average throughput density of 684.9 vehicles per hour, or 1 vehicle every 5.26 seconds during peak traffic periods. This volumetric flow rate represents logistical infrastructure performance parameters, unprecedented in military river crossing operations, eclipsing historical precedents by orders of magnitude. To contextualize this achievement within comparative frameworks, Napoleon's Grande Armée, crossing the Niemen River in June 1812, required 3 days to transit approximately 45,000 personnel and associated equipment across pontoon bridges spanning 180 meters, yielding an effective throughput of 15,000 personnel per day per bridge. The Wesel crossing, by contrast, sustained throughput equivalent to transporting an entire mechanized division, 12,000 personnel plus 3,847 vehicles of varying classifications every 8.7 hours. The mathematical escalation reflects not merely incremental improvement, but fundamental transformation in how industrial societies project military force across geographical obstacles. The Wehrmacht's defensive architecture in the Ruhr sector undergoes catastrophic systems failure as this logistical throughput translates into operational momentum. German defensive doctrine, codified in Oberkommando des Heeres operational directives dating to 1943, predicated Ruhr defense on maintaining coherent defensive lines, anchored on the Rhine's western bank while conducting systematic demolition of industrial infrastructure to deny Allied exploitation. This strategic calculus presumed Allied crossing operations would require 7 to 10 days to establish sufficient bridge infrastructure for sustained offensive operations, providing Wehrmacht forces adequate time to implement scorched earth protocols across critical industrial facilities. The actual temporal compression from zero crossing capability to full army-level logistics in 48 hours created decision cycle disparities that rendered German defensive planning operationally irrelevant. By March 28th, elements of the U.S. 2nd Armored Division had penetrated 23 kilometers east of the Rhine, bypassing prepared defensive positions that German units were still attempting to occupy. The dislocation cascaded through Wehrmacht command structures, LXXXVI. Corps headquarters transmitted situation reports, describing complete loss of defensive coherence and inability to establish blocking positions due to Allied advance, velocity exceeding reconnaissance and deployment capabilities. Field Marshal Walter Model, commanding German Army Group B, documented the strategic implications in communications to Oberkommando der Wehrmacht. On March 29th, the Rhine barrier has been penetrated at multiple points. American engineering capacity permits bridge construction velocities that render river demolition strategies ineffective. Request immediate authorization for tactical withdrawal to secondary defensive positions. The response from Berlin reflected strategic delusion, divorced from operational reality orders to defend the Ruhr. To the last man arrived as American armored columns were already enveloping Essen and Dortmund from multiple axes. The industrial core of Nazi Germany's war economy entered terminal phase within 96 hours of the Wesel Bridge becoming operational. The Ruhr Valley, producing in 1944 approximately 125 million tons of coal and 4 million tons of steel, annually ceased meaningful production by April 8th as Allied forces completed encirclement operations. This represented more than tactical defeat. It constituted systemic collapse of the industrial infrastructure, sustaining Wehrmacht operations across all theaters. The Rhine, which German military planning had designated as the ultimate defensive barrier, functioned instead as an accelerant to strategic disintegration. The river that was supposed to buy time instead compressed it, transforming geographical advantage into logistical liability, as German forces found themselves trapped against the same water barrier they had once considered protection. The Rhine crossing at Wesel represents a tactical operation, yet its significance transcends immediate battlefield outcomes to illuminate fundamental transformations in how industrial societies prosecute organized violence. The 48-hour bridge construction timeline, when subjected to rigorous analytical decomposition, reveals underlying organizational architectures that converted material abundance into operational tempo, a conversion efficiency that constituted strategic asymmetry, more decisive than any weapons system deployed during the European campaign. Consider the logistical infrastructure that enabled the Wesel operation. U.S. Army engineer units operating across the Western Front in March 1945 comprised approximately 2,400 personnel distributed among 47 separate engineer combat battalions, 14 heavy pontoon battalions, and 31 specialized bridging companies. This force structure represented 3% of total Allied ground forces in theater, yet generated disproportionate operational impact through systematic application of standardized engineering protocols developed across 3 years of combat operations spanning North Africa, Italy, and Northwest Europe. The material prerequisites for a single Class 40 pontoon bridge, 40 flotation units, 847 treadway panels, 3,200 meters of anchor cable, existed as pre-positioned inventory items manufactured to specifications, established by the U.S. Army Corps of Engineers Equipment Development Program initiated in 1940. This standardization philosophy enabled interchangeability across continental supply chains. Pontoon units fabricated in Pennsylvania, proving functionally identical to units produced in Illinois, both conforming to dimensional tolerances of plus or minus 3.2 millimeters, despite originating from facilities separated by 1,127 kilometers. The mathematical framework underpinning this logistical architecture becomes apparent through comparative resource allocation analysis. Wehrmacht engineer units organized under pioneer battalion structures possessed equivalent technical expertise and doctrinal training. Yet German bridging operations confronted systemic constraints deriving from industrial base fragmentation by 1945. German pontoon bridge production occurred across 17 separate facilities, utilizing non-standardized manufacturing protocols that generated component variations, requiring field modification during assembly modifications, consuming an average 7 additional man-hours per bridge section according to captured Wehrmacht engineering logs. The temporal implications compound exponentially. A German pioneer battalion, constructing a 350-meter Rhine crossing under optimal conditions, defined as absence of enemy interdiction and favorable weather, required estimated 96 to 120 hours based on Heeresdienstvorschrift engineering manual specifications. The American capacity to achieve equivalent outcomes in 48 hours represented not 50% improvement, but rather 100% increase in operational tempo, effectively doubling the velocity at which ground forces could exploit river crossing opportunities. This velocity differential translated into strategic compression of decision cycles. Wehrmacht operational planning predicated defensive preparations on multi-day Allied bridging timelines, creating temporal windows for repositioning reserves, implementing demolition protocols, and establishing secondary defense lines. The actual 48-hour construction cycle collapsed, these windows generating cognitive dislocation within German command structures that manifested as operational paralysis units, receiving orders to defend positions already bypassed. reserves directed toward sectors already penetrated demolition teams, arriving at industrial facilities already under Allied occupation. The systemic insight transcends individual operations. The Wesel Bridge exemplified organizational architectures, where material abundance combined with procedural standardization generated compound effects exceeding simple arithmetic. Addition. 20,000 engineers did not represent merely 2,0,0,0,0 individuals, but rather 2,0,0,0,0 nodes within an integrated logistical network, each node's productivity amplified through standardized training protocols, interchangeable equipment specifications, and synchronized operational procedures. The Wehrmacht faced not superior soldiers, but superior systems, organizational frameworks, optimized through industrial management principles, where efficiency gains accumulated recursively across hierarchical integration layers. The bridge itself stood as physical manifestation of these abstractions. 351, 4 meters of steel and canvas spanning water, yet functionally representing the material expression of organizational capacity, differential between industrial systems operating at fundamentally different optimization levels. The human dimension of the Rhine crossing operation persists through documentary evidence that resists systematic quantification, yet illuminates operational realities obscured by statistical aggregation. Post-war historical research programs, including the U.S. Army's Historical Division interviews conducted between 1946 to 1948 compiled testimonial accounts from 347 engineer personnel who participated in Rhine bridging operations. These primary source materials reveal phenomenological experiences that technical documentation necessarily excludes: the sensory environment, psychological states, and subjective temporality of men operating within industrial warfare. Mechanical rhythms. Corporal Walter Simmons, 502nd Heavy Pontoon Battalion, recorded observations during post-war debriefing sessions that capture the acoustic landscape. The sound never stopped. Hammers on steel, you hear it in patterns like a factory shift, but underneath there's the artillery. You learn to distinguish them by sound signature. The outgoing shells have a different pitch than incoming. Eventually, it becomes background noise, like working near railroad tracks. This auditory habituation reflects psychological adaptation mechanisms documented in industrial psychology research, sustained exposure to high decibel environments. Rhine crossing operations generated ambient noise levels, averaging 95 to 108 decibels, producing sensory threshold adjustments, where stimuli requiring immediate attention separate from background constants through pattern recognition rather than absolute volume discrimination. The olfactory environment comprised distinctive chemical signatures, diesel fuel combustion products from generator units, producing the characteristic mercaptan odor of partially oxidized hydrocarbons, Rhine River waters mineral, composition generating ferrous oxide scents, particularly pronounced in shallow water zones, where pontoon anchoring operations disturbed sediment layers accumulated over centuries, and cordite residue from artillery propellant, nitrocellulose-based compounds producing acrid nitroglycerin decomposition, byproducts detectable at concentrations below 2 parts per million. Private First Class Donald Chen, 164th Engineer Combat Battalion, noted in personal correspondence. The smell stays with you. You can't wash diesel and river mud out of your uniform, and after 48 hours you stop noticing it on yourself, only on men rotating in from reserve positions. Technical Sergeant Raymond Burke's post-war memoir contains the observation most frequently cited in subsequent historical analysis. It wasn't heroism, it was work. And we worked until there was nothing left to build. This statement encapsulates a philosophical distinction between individual agency and systemic momentum. The operation's completion, deriving not from exceptional individual performances, but from sustained application of procedural protocols across distributed workforce units. The psychological framework resembles industrial production models more than traditional martial valor success, measured through throughput metrics, quality control tolerances, and schedule adherence rather than tactical brilliance or personal courage. Civilian populations in villages within visual range of bridge construction sites, Bislich, Buderisch, and Fluren communities, sustaining war damage from Allied bombardment, yet maintaining habitation, observed the operation with reactions documented through post-war German oral history projects. Margarete Hoffmann, age 23 inches, March 1945, recalled, "We watched from upper floor windows. The speed was unbelievable, like watching a road appear across the water. My father said, 'This is what defeat looks like. Not explosions, but construction.'" The Rhine, throughout its documented human history, spanning Roman occupation forward, functioned as boundary mechanism, geographical, political, cultural. In March 1945, it transformed into transit infrastructure, carrying not merely vehicles and personnel, but the material expression of systemic capability differential between collapsing and ascendant industrial orders. The operational aftermath of the Wesel crossing illuminates warfare's transformation from attrition-based confrontation to logistics-mediated systems competition. Within 72 hours of bridge completion, Allied forces operating east of the Rhine achieved penetration depths averaging 34.7 kilometers across a 180-kilometer frontage, advance velocities that Wehrmacht defensive planning had calculated as requiring 12 to 15 days under conventional operational parameters. The bridge infrastructure itself sustained continuous utilization through April 18, 1945, facilitating an estimated 284,000 vehicle movements, representing approximately 847,000 tons of military equipment, supplies and personnel. This throughput density generated operational momentum that transformed tactical river crossing into strategic dislocation. German defensive coherence in the Ruhr pocket collapsed not through battlefield defeat, but through logistical strangulation as supply lines extending eastward from Rhine crossings enveloped Wehrmacht units, faster than German command structures could process intelligence regarding Allied positions. The engineering accomplishment transcended immediate tactical utility to demonstrate organizational capacity differentials that determined strategic outcomes independent of battlefield performance metrics. The 48-hour construction timeline represented not extraordinary individual effort, but rather systematic application of standardized protocols across integrated logistical networks, a capability profile reflecting industrial base characteristics where material abundance combined with procedural optimization generated compound operational advantages. History would subsequently emphasize dramatic battlefield engagements. Remagen's captured bridge, the airborne operations at Wesel, armored thrusts into Germany's interior. Yet the unglamorous infrastructure enabling these operations, pontoon bridges built by exhausted engineers under artillery fire, operating within industrial timeframes that transformed geographical obstacles into temporary inconveniences, constituted the actual mechanism through which strategic advantage manifested. The Rhine crossing succeeded not through tactical brilliance, but through organizational capacity, operating at scales that rendered individual battlefield outcomes increasingly peripheral to systemic momentum. The Rhine had guarded Germany for 1,000 years, a geographical constant that defined empires, anchored defensive doctrines, shaped the trajectory of European history itself. But in March 1945, it bowed to the will of men who refused to accept geographical determinism as strategic inevitability. Within 48 hours, they transformed a natural barrier into industrial infrastructure, converting hydrological obstacle into logistical highway through systematic application of organizational capacity, operating at scales that rendered individual tactical interventions statistically irrelevant. They changed the course of a war not with bullets, but with bolts, not through battlefield heroism, but through procedural precision, sustained across distributed networks of human labor operating within mechanical rhythms that industrial civilization had made possible. The river yielded, and with it, history.